Waves, day 4. Once again, a wave is a vibration that transmits energy without transmitting a physical material. Now, most objects have what is called a natural frequency. A good example is like the tuning forks we had in class. The 256 hertz tuning fork. If I strike the 256 hertz tuning fork, it will automatically every time vibrate at 256 hertz, plus some multiples of that mixed in, like 512, which is 2 times 256 hertz. But its predominant frequency, its vibrational frequency, will naturally be 256 hertz. It does not want to vibrate at 296 hertz. You can force it at 296 hertz, but that would take a lot of effort, a lot of energy. That's called a forced vibration. When you try to force something by controlling it from the outside, it does not naturally want to do that. Now, things will resonate if you tune in to the use a forced vibration to match the natural frequency. When you do that, you get a large amplitude in the vibration of the object. That's called resonance. So when the forced vibration matches the natural frequency. One of the more extreme examples we showed you in class was the video of the Tacoma Narrows Bridge here on the right. If you didn't see it in class, go to YouTube, look it up, just punch in Tacoma Narrows Bridge collapse, and you might want to show that to your parents. It's pretty awesome. Because that's a steel and concrete bridge, and the wind that was blowing that day wouldn't even knock over a person. It was like about a 40-mile-per-hour wind, but the way it was blowing and swirling around and blowing over the bridge itself, and it's more complicated than we need to get into right now, but it caused the bridge to twist and swing at its natural resonant frequency. So it didn't take a whole lot of energy from the wind to get the bridge to sway and sway and sway and then break and crack and fall down. That's resonance. The other example I used was brain waves, quote unquote. Like this example on the left with pendulums, you can see here that there are 2 pendulums that will have the same frequency, number 1 and 4. In other words, if I were to swing pendulum number 1, number 4 would also start up. If they're connected at the top by the same bar, they would resonate with each other. Swinging one would cause the other one to start swinging eventually. The other 3, numbers 2, 3, and 5, would not be resonating with numbers 1 and 4 because they have the same tendency to swing at the same rate. Beats are a frequency that results from alternating constructive and destructive interference patterns when 2 notes of slightly dissimilar pitch are played simultaneously. Musicians use this to tune their instruments. Eliminating beats brings 2 notes into tune with each other. And I showed you an example of that in class, but let me remind you here on the next slide. So let's look at this bottom diagram here. Let's say, first of all, these 2 tuning forks are both at 256 hertz. They will resonate with one another. And I did this in class. If you strike either one of these, but if I strike the tuning fork on the left and let it vibrate for a little while, just the motion of the air particles, the vibration of the air particles will set the second tuning fork into vibration because they resonate with each other. It doesn't take a whole lot to make a tuning fork of 256 hertz vibrate if you are forcing it at 256 hertz. But let's say that this second tuning fork is not 256 hertz. Let's say it's 258 hertz. So they're slightly out of tune. Now if we played them together, you would get what are called beats, as I mentioned before. In class I called them woo-woos. Woo. Anyway, the graph here on the right-hand side might illustrate this. Let's ignore the units. There really are no units on here, so that's good. Let's say this top one represents 258 hertz, a frequency of 258 hertz. And the bottom one represents 256 hertz. Let me use red. 256 hertz. Well, what's going to happen here is every so often those 2 notes will be in tune with each other. That's represented right here in location number 1, where if you add the 2 waves together, crest meets crest and trough is meeting trough, so you have constructive interference. Also over here at position number 4, you have constructive interference. That's going to be the loud part of the beat. Well, in between the 2 loud parts, over time, what happens here in position number 3, I'll use blue. Okay, for the 258 hertz wave at the top there, you're at a crest, but if you follow that blue dash downward, or the actual dash in the actual diagram, the black dash, you're going to have the crest of the 258 match the trough of the 256, so you get destructive interference. So what you have here is an alternating pattern of the two waves superimposed with each other, having constructive and destructive interference. So you get loud, soft, and we keep on going here. But we say the beat frequency, in this particular case, because they're off by 2 hertz, the beat frequency is 2 hertz, and it's simply just subtraction. In other words, if one of these two tuning forks was 260 hertz, the other was 256 hertz, there would be a beat frequency of 4 hertz. I'm told that the maximum amount that can be off by is about 10 hertz. The human being cannot distinguish more than a 10 hertz beat frequency. So to recap one more time, a wave is a vibration or disturbance that transmits energy without transmitting the material substance. We have mechanical waves that require a medium, like water waves, sound waves, and we have electromechanical energy or waves that can transmit without a medium, like light, X-rays, gamma rays, radio waves. And then we have the other categorization of waves, and that is longitudinal versus transverse. Sound waves are longitudinal. The particles of the medium, whether it's air or water or steel, the particles vibrate parallel to the way the wave is transmitting. In transverse waves, the classical way we draw waves like water waves and light waves is the particles or the fields oscillate, vibrate perpendicular to the way the wave is transmitting. And then we have resonance. Resonance is a phenomenon where a large amplitude of vibration occurs with very little energy input, so that you get dramatic results when you match the force vibration to the natural tendency of the object to vibrate at its natural frequency.